Lesson number 2 in the Factoring and Applications chapter looks at factoring trinomials of the form ax squared plus bx plus c. So it answers the question, how do you factor when you have a number in front of the x squared? And you can't remove it as a GCF, because that's what we did in the last lesson. We removed that factor as from each term. So what I want you to do first is I want you to complete the following. I want you to expand this out. So multiply 2x plus 1 by 3x plus 4 and 3x minus 2 by 4x plus 3 using the distributive property, or sometimes commonly called FOIL. So press pause and do that for me. So if you expand this out correctly, what you will get will be 6x squared plus 11x plus 4. There's my 6x squared, there's my 4, and my 11x I get with the 3x and the 8x. If I expand the bottom one out, I will get 12x squared plus x minus 6. There's my 12x squared, there's my negative 6, and my positive x comes from 9 minus 8. So if I expand this out, what it means is if I start off with 6x squared plus 11x plus 4, it will factor down to these two factors. And the same thing here, 12x squared will factor to 3x minus 2 and 4x plus 3. So when we go to factor trinomials of this nature, there's two methods that we can use. We can use the method of decomposition, which is what I'm going to show you next, but we can also use inspection. Kind of not the same inspection with the product and sum charts that we used in the last lesson, but an inspection of how does this create that. So how do I get the 6x squared? By multiplying the first terms. How do I get the 4? By multiplying the last terms. And then how do I get this 11? So we'll look at a strategy for doing those types of questions. So if we go back to decomposition, this is a review from last year. This is actually part of what we did in 10 Common. So if I look at the polynomial expression represented by the group of algebra tiles here, what would I get? So take a moment to write that down. I get 2x squared plus 7x plus 6. Now, if I was to arrange the algebra tiles into a rectangle, what would I get? So take a moment to think, to see if you can do that. So if I was to try to arrange these as a rectangle, what I would need to start off with is I would put my two squares side by side, or I could put them one on top of the other, but given the space that we have, side by side. And then I'm going to take one of these X tiles and I'm going to turn it this way. And then I'm going to take another one and turn it this way. And then I can pull this one over. And when I do that, now I can put this in place. I could put another one over and put this in place. Then from here, I've got 3 left over, so I could put 2 here and 1 here. So there's 1, 2, and 3. And if I've done that correctly, these ones I should be able to slide into place so that all together, by the time I'm done moving all of my shapes, I get a rectangle length by width. The length of this rectangle, each of these squared units has a measurement of x by x. That's how I get the x squared. And I have 2 of them. So that gives me 2x. Each of these has a width of 1 because it matches up to these little 1 tiles. It's a 1 by x. So this would be 2 x's plus 1, 2, 3. And then if I go down the side, this length here is another x. And then I have two more, x plus 2. And if you were to FOIL this out, you would see there's my 2x squared, there's my 6, and 4 and 3 gives me my 7. So that's using decomposition. If you want to take a moment, class example number 5 with 5x squared plus 7x. Try to see if you can do that one, and I'll put the solution up. There's my arrangement of 5x squared plus 7x plus 2. So if I go to factor this, I look at the length. I've got x, 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 and x. So I have 5 of those x's. These are 1 and 2, so 5x plus 2. And then the width would be an x plus 1. So I can use this method for a lot of different trinomials that have this number or coefficient in front of the x squared. But it starts to become tedious, and if I have too many squares, if I have like an 8x squared or 11x squared, it takes a lot of room. So we want to try to find another more algebraic method or solution. And we can use what we did in the last section with the product and the sum. Only this time when we talk about the product and sum, the sum is still my middle term. It's still that 11x. So in this example, what we're looking at, up at the top, we factored 6x squared plus 11x plus 4 to get this. And what we did with the 11x is we actually broke it up into 3 and 8. And that allowed us to do the factoring by grouping. 6x squared and 3x have a 3x in common, leaves me with 2x plus 1. 8x plus 4 has a 4 in common, which also leaves me with a 2x plus 1. There's my 2x plus 1, and here's my 3x plus 4. But why did we choose 3 and 8x? That's the question. How do we figure that out? Well, how are the numbers 8 and 3 connected to 6 and 4? Because before, when we were doing our product and sum chart, the sum was the middle term, so I get the sum of 11. But how do I get the 8 and 3? I know 8 plus 3 equals 11. But how do I get that connection to the 4? Or is it just the 4? Well, it's not. It's the 6 and the 4 with a relationship with the 8 and the 3. And that relationship comes in the product. 6 times 4 equals the same value as 8 times 3. So the question that we're answering is two numbers that multiply to 24 and add to 11. That gives me the 8 and the 3. If we do this again, we have 12x squared plus x minus 6. So again, if I looked at my product and sum chart, my sum is still 1, but my product this time, again, if we looked at what we split it to, we had split it into a 9x minus 8. Why 9 minus 8? Well, I know right now that 9 plus negative 8 equals 1. There's my sum. But my product, 9 times negative 8 equals negative 72. And negative 72 is the same as 12 times negative 6. So the difference between what we did in the last lesson with our product and sum chart and in this lesson is we multiplied the first term and the last term. Now if I just take a moment to go back to the last lesson, if we look at the polynomials that we were dealing with in the last lesson, we had things like x squared plus 5x plus 6. Well, if I use this idea of multiplying the first and the last term, does that still work in the last polynomial? Sure it does, because this was a 1. So we just don't think about the fact that we multiplied these together because this is a 1, so it doesn't really play into changing the multiplication. I just get the last term. But when I have a number in front, I have to multiply. I have to include that in front. This becomes the method of decomposition. So when we look at the method of decomposition, I'm actually going to skip to certain questions on class example 3, 4, and 5. So I'll start off with 3A, I'll do 4A, and then I'll do 5A. And then the rest of the questions, I'll show you the other method that we can use. So with 3A, if I look at my product and sum chart to do decomposition, my sum is 7, and my product becomes 2 times 6, which is 12. So I need two numbers that multiply to 12 and add to 7, 3 and 4. Then what I do with the 3 and the 4 is I rewrite 7x as 3x plus 4x. And it doesn't matter which one I put first and which one I put second. Although if I look at my numbers 2 and 6, I should look at them and think, you know what, 4 goes closer with 2, and 3 kind of matches up with 6 because of those common factors. Once I do this part in here, this decomposition, then I go back to the factoring by grouping. So I take 2 terms at a time, I factor out what's common. So these 2 terms have a 2x in common, these 2 terms have a 3 in common. Now I'm left with another common expression, or common factor of x plus 2, and 2x plus 3 is what remains. That's decomposition. So take a moment, press pause, and see if you can do class example 4A following the same steps. So again, if I look at my product and sum chart, the sum is going to be 17, the product is going to be negative 18. So 2 numbers will multiply to negative 18 and add to 17, 18 and negative 1. And again, it doesn't matter which one I group where. 6x squared plus 18x minus x minus 3. Look at the first 2 terms, I can factor out a 6, and I'm left with an x plus 3. And then if I look at the next 2 terms, what I'm trying to get is I'm actually trying to get an x plus 3. That's what my goal is to factor something out of these 2 terms so that I'd be left with a positive x and a positive 3. Well, that would be factoring out a negative 1. X plus 3, 6x minus 1 becomes my answer. Class example number 5, keep it the way that it is in that order. Leave the y squared at the back. Don't try to move it to the front. Same system, product and sum is going to be negative 7 and negative 30. So again, if you want, press pause, take a moment to try to go through this question, and then I'll go through the answer. So 2 numbers that multiply to negative 30 and add to negative 7. Oh, I've got that backwards. Add to negative 7, multiply to negative 30. So my 2 numbers become 10 and 3 because the difference between them is going to be 7, and the multiple will be 30. And because this is a negative 30, that's how I knew to make this a difference. To make it a negative 7, I make that a negative 10. So I've got 15 minus 10y minus 3y minus 2y squared. Common to these 2 terms is a 5. Leaves me with 3 minus 2y. Oh, there should be a plus 3y. There we go. And if I look at these 2 terms, what I have in common is a positive y leaves me with 3 minus 2y again. So my 2 polynomials. So again, to finish off this question, I had factored out a positive y from my second 2 terms, left me with a 3 minus 2y. So 3 minus 2y became my common factor of these 2 terms, and I was left with a 5 plus y. This is the method of decomposition. It will work no matter what the polynomial or the trinomial, that's when we use this, no matter what the trinomial is when it has a coefficient in front of my y squared, x squared, my squared value. However, there's another form that we can use. We can do this by inspection. When we do this by inspection, the best way to do these questions by inspection works if one of 2 things. Either the first term or the last term has to be a prime number. If it's not a prime number, I could still use this inspection method. It's just going to be a little bit more tedious. So because 5x squared and 2 are both prime numbers, this is an excellent example of a question that I could just factor without having to do all of that work. Because when I factor this, I know that I should get 2 binomials. And the thing that I should know, the other part that I should know, is when I multiply the 2 binomials together, the first term and the first term is going to give me a 5x squared. And I know that each term has an x in it. So the only way that I can get a 5x squared is I have to leave this as a 5x and an x. That's the only way I can get a 5x squared, which is why it works nicely for prime numbers. Then when I look at the last term, it's a 2. Well, the last term I get from multiplying these 2 together. And the only way that I can multiply them together to get a 2 is 2 times 1. The only question I have to answer is, do I put the 1 here and the 2 there? Or do I put the 2 here and the 1 there? And for that, I have to look at the middle term. If I put 1 and 2, I will get 10 and 1, which gives me 11. Didn't work. So instead, if I put the 1 and the 2 like this, I get 5 and 2, which gives me 7. So this does take some mental math skills to tie this together, and it really tests your understanding of how do I expand this out. How do I go from 5x plus 2 times x plus 1 to get this expression? And that goes with my first terms, and then I have what I call my outside terms, my inside terms, and my last. My first terms give me my first term, my last terms give me my last, and the outside and the inside give me my middle, so that I can break this up. So now if we look at class example 4b, 3n squared minus 2n minus 8. Because the 3 is a prime number, I can choose this method. Because I know that in order to get 3n squared, I have to have 3n times n. The negative 8, that becomes a little bit more tricky, because in order to get 8, I can have 8 times 1, or 1 times 8. I can have 4 times 2, or I can have 2 times 4. And to add more complexity, because this is a negative 8, I know that within each of these groupings, one number has to be positive, one number has to be negative. And I have to put it in such a way that go my outside and my inside, I will get a negative 2. So take a moment to look at this question and kind of figure out, okay, so how could I get that negative 2 in these combinations? So just quickly, if I look at this being 3 times 8, I'd get 24 and 1. The difference of 24 and 1 is going to be 23. That's not going to work. If I go 1 here and 8 here, I'm going to get 3 and 8, which is going to give me a difference of 5. Doesn't work. If I put 4 here and 2 here, I'm going to get 6 and 4, the difference of which is 2. So 4 and 2. To get my negative 2, I need a negative 6 and a positive 4. The negative 6 from here and the positive 4 from here. So it does take some work, but it is doable. If you want to do decomposition, continue with decomposition. But if you recognize that you have a prime number to work with, you can work with that prime number. So if we look with C, C is a bit different from the previous two because in C, it's the last term. That's the prime number. And technically, it's not even really a prime number because 1's not a prime number, but 1 is a number that I know the only way I can get it is to go 1 times 1. Now, if I look again at this question, this is a negative 8, and this is a positive 1, which means these two have to be negative. Now I'm on my start. Now I need my 12x squared. So to get 12x, this is where it becomes a little bit more work because I've got 12 times 1, which could be 1 times 12. I've got 6 times 2, or 2 times 6. And I've got 4 times 3, or 3 times 4. And I need to put them into this equation. And I need to put them in such a way that when I go the outside and the inside, I'm going to get a negative 8x. Well, because both of these end with a negative 1, I can eliminate these because it won't matter if I put the 4 here and the 3 here, or the 6 here and the 2 there, or vice versa. When I multiply them out, I'm still going to get the same combinations. So if I try putting a 12 and a 1, I'm going to get 12 and 1. Because they're both the same sign, I'm going to add them together. Gives me 13. If I put a 6 and a 2, 6 and 2 together gives me my 8. So I've got a 6x and a 2x. There's my negative 6, negative 2 gives me my negative 8. So it does take some practice. It takes some work. If I look at class example 5b, 5x squared, or 15xk squared plus 5k minus 10. First step in doing any of these questions should be to look for a GCF. Can I take something out of each term? I can take a 5. Oops. Factored that correctly, that would work better. So if I take out a 5, I get 3x squared plus 3k squared plus k minus 2. 3 and 2 are both prime numbers. It's a great one to factor by sight. Because in order to get a 3k squared, it's going to be 3k times k. And in order to get that 2, I can only use 2 times 1. I just need to figure out where to put the 2 and where to put the 1, so that the middle term becomes 1. And in order to get that negative 2, one of those numbers has to be positive and one has to be negative. So when I'm doing my outside and my inside, I would be subtracting them. So if I put the 2 here and the 1 here, I get 6 and 1, which gives me a 5. If instead I go 2 and 1, I get 3 and 2. The difference is going to be 1. I want a positive 3 and a negative 2. Okay? Class example number 6 just throws in an extra variable. Instead of just having x squared, I now have an x squared and a y squared. I can factor these using the exact same methods as before. In this one, because I've got a prime number here and luckily enough a prime number there, I can use my inspection. The only way I'm going to get a 2x squared is 2x and x. The only way I'm going to get a 2y squared is I have to have a 2y and a y. And the only thing I need to now determine, because this is positive and this is negative, these both have to be negative, but where do I put them? I have to put them in such a way that when I go outside and inside, I'm going to get a 5 in the middle. So with the way that I've written them right now, I get a negative 2xy and a negative 2xy, which doesn't give me the 5. So I have to switch them around. Negative 2y and negative y. Negative 4xy, negative xy, there's my negative 5. And when I multiply these two out, there's my 2y squared. So adding that extra variable at the end does not change how we finish up the question. It just adds an extra component to the question. So if I look at B, our last one, before you have some practice questions, I have 2n and n. That's how I'm going to get 2n squared. With 35, I've got the arrangement of 35 and 1, or 7 and 5. Those are the two ways I can get 35. Well, 35 and 1 I should eliminate because those numbers are going to be too high when I try to put them in here. So now I have the 7 and the 5. And I have to figure out which way should I put them so that I get a 3. And if I look at it, 2 times 5 is 10. 7 times 1 is 7. And then what's left over would be 3. 10 minus 7. So in order to get a negative 3, I would need a negative 10 and a positive 7. And then to get the m squared, this would have to be m, and this would have to be m. There's my negative 35m squared. There's my 2n squared, negative 10 and 7. There's my negative 3nm. So what I'd like you to do is spend about 10 minutes working on these questions. 3, C and E, 4, A and D, 5, 6, D and E, and 7, D. Then when you're done, go on to the next part of the lesson and we will look at perfect square trinomials. So in the last lesson, or in lesson number 1, we looked at a difference of squares. We looked at how do I recognize a difference of squares. Well, the first number is a perfect square number, the last number is a perfect square number, and the sign in the middle is a minus. The other type of polynomial that we have is a perfect square trinomial. In a perfect square trinomial, we have the product of two identical binomials. So if I take a look at p plus q squared, that means p plus q times p plus q. So when I go to expand this out and use the distributive property, I get p times p, which is p squared, then I get my outside, which is a PQ, my inside, which is another PQ, so now I have two of them, and then my last term, the Q squared. When it is written in this form as P plus Q all squared, the most common mistake that is seen is forgetting this inside term. Because we square the first and we square the last, but we forget that when it's expanded out, I have this part of the distributive property still to finish. So what I recommend is when you see it like this, you rewrite it as P minus Q times P minus Q. And then that way when you go to expand it, to distribute it out, I get P times P, which is a P squared. I get a negative PQ and a negative PQ, which gives me two of them, and a Q squared. So from this patterning, what we should be able to see is that the first term in the trinomial is the square of the first term in the binomial. So, first term. And the last term in the trinomial is the square of the last term in the binomial. And then the middle term. How do I get this middle term? Well, if I go p times q, I've got the product. And then if I double it, I have double the product. So the middle term is double the product of the first and the last terms. So in a perfect square trinomial, the first and the last terms have to be perfect squared numbers. So can I take the square root of x squared? Yep. Can I take the square root of 25? Yep. If I do that, I get an x and I get a 5. If I multiply those two together and double it, do I get 10x? Yep. This becomes my perfect square. So this is how I would then write it. So I need to be able to recognize that it's a perfect square trinomial, and then I need to be able to factor it. Now, if you didn't recognize that this was a perfect square trinomial, could you still factor it? Yeah, you can still use the methods that we did, the factoring by inspection with the product and sum charts, the decomposition, the site inspection that we did with the prime numbers. You could still use those methods. This is just recognizing this type of trinomial that you have and shortcutting it. So if I look at class example number 7, which of the following are perfect square trinomials? So, can I take the square root of a squared? Yes. Can I take the square root of 4? Yes. I get an a and I get a 2. If I multiply them together and double it, do I get 4a? Yes, I do. That's a perfect square trinomial. If I look at b, can I square root x squared? Yes, I get x. Can I square root 6? Well, I can, but it's not very nice. So we actually say no, we can't. So this is not a perfect square trinomial. When we ask if we can square root it, we mean, is it a perfect square? Does it give us a nice number when we square root it? So we look at C. Can I square root 4x squared? Yep. Can I square root 81? Yep. 2 times 9 is 18. Double it. Do I get 36? Yes, I do. To get a negative 36, I'd make that a negative 9. Negative 9 times negative 9 will still equal a positive 81. So this is a perfect square. If I look at the last one, can I square root y squared? Yep. Can I square root negative 16? No. I can't square root a negative number. This is not a perfect square. It looks like it should be, because if we're not paying attention to that negative in front of the 16, we could end up looking at it going, yeah, I can square root 16, I get a 4. Y times 4 is 4y, double it, I get 8, we're good to go. But this cannot be negative. In a perfect square trinomial, your first term and your last term must be positive. If they are not positive, it is not a perfect square. So in class example number 8, we want to fill in the blank to make this a perfect square. So to fill in the blank, square root the first, square root the last, multiply them together, and double it. So double of 10x is 20x, or it could be a negative 20x, in which case when I go to factor it out, I would get a negative 10 and a negative 10. So let's look at C. Square root the first, square root the last, multiply these two together, which gives me 30, double 30, and I get 60. Now in the last one, I'm missing the last term. So I square root this and I get 3. To get the 24, I know that I had to go 2 times 3 times something. What is that something? 2 times 3 is 6. 6 times what equals 24? It's 4. So then to get my last term, I'm going to take the 4 and square it, and I'll get 16. So now I've had a little bit of practice, we're going to factor these. I have to check, is this a perfect square trinomial? Can I square root the first? Yes, I get 7x. Can I square root the last? Yes, I get a 1. If I multiply these two together, I get a 7x. When I double it, do I get 14? I do. To make this a negative 14, I make this a negative 1. And then I write it squared. So if I look at B, square root the first, and I get 4. Square root the last, and I get 5x. Multiply them together, I get 20. Double 20, and I do get my 40. So now if I look at the last one they threw in a fraction. If I take the square root of 1/9, it's the same as the square root of 1 over the square root of 9, which becomes 1/3. So I get 1 over 3 times 8. If I square root 9b squared, I get 3b. If I multiply 1/3 and 3 together, I get 1. If I double 1, there's my 2. To make it a negative 2, I make this a negative 3b squared. So now I would like you to look at question number 9. Factor only the perfect squares. So if it's not a perfect square, don't factor it. And then questions 12, 13, and 15. Don't forget to check the sideboard for important dates for this week, and we will see you in class tomorrow.